So welcome to 626 time series and 685 directed studies. Let's start with the latter first. So earlier today, Kim Ritchie posted on my behalf the following directions for the capstone project 8-minute update number 1 for this semester. You can find that on eCampus under 685 course notes and documents. So that will happen next week, and if you look, it's very similar to what the last update was in the previous semester. We need a project title and your name. We need the Mises tree and key question. Now, most project coaches can probably recite without any notes each of the first 2 slides for each of their projects they're supervising. And then what feedback have you incorporated? Where is the data? At what stage are you with the data? Do you have all the data? Do you have a plan for all the data? So you might be doing a time series project and you have up to the end of August 2017. And you're going to add more data. Okay, that's fine. What models have you built? And in particular, we're always interested in the validity of these models, and so let's see some output which demonstrates that the models you are fitting are valid. If there are some invalidity issues, that means we need to modify the model. And then what have you learned thus far? So let me tell you, to the 2 groups that I run, here's what I'm going to do. I am going to run each student's slides. So when we get to slide 1, and I've seen all that before, yep, got that. Slide 2, the speed, yep, got that. Slide 3, your data's in good shape, yep, got that. Slide 4, okay, the models. All right, for student number 1, it's about the models. So, and given your feedback that you weren't interested in peer feedback as much as coaches' feedback, we've changed this semester to focus more on coaches' feedback, and you'll get a detailed meeting with the coach the next week. So if your project is in really good shape, your meeting will be quite short. It'll still go the regular time. If you've got issues that are serious, then we'll have to have a meeting. I plan for my groups to have an initial meeting saying, there's issues about A, B, and C. Please do this for me, and then in the next week we're going to have another follow-up meeting. Okay. Any questions or points of discussion about stat685 and what you've been asked to do? So, as a reminder, you have to defend after spring break, so the second half of March before early April. So we've really essentially got the holiday break from mid-December to mid-January, and then 1 semester, half of this semester and half of the next. So we're getting to the serious end of the business. Okay. Given that there are no questions with that, let's go over to time series. And tonight we're going to talk about putting autoregressive models together with moving average models and having the combination autoregressive moving average models. It turns out that you can model a large part of the world using these so-called ARMA models. Okay, so Erica, I just got a note saying it's hard to hear me. Is that true? Okay, let me increase my volume here. All right, so in this topic we consider models, and we want to model the current value of y at time t is modeled as a linear function of earlier values of yt. That's the autoregressive part, and earlier values of the error term. A, that's the MA piece. So let's take the simplest autoregressive moving average model, namely when the autoregressive order is 1 and the moving average order is 1. So equation 1 gives us the mathematical definition of an ARMA 1-1. So this piece here, right, is the AR piece. And this piece here is the MA piece. So we've just pasted both bits together. And typically what we rewrite one is, we can rewrite that into two pieces. This is the error part. And this is the part that involves Y. Now recall, for the autoregressive part to be stationary, we need C1 to be between -1 and +1. So remember the correlation between YT and YT minus 1 is phi, 0.9 say. YT and YT minus 2 is phi squared, 0.9 squared. So for that to die off, we need the number to be less than 1 in magnitude. Now, the MA part, for that to be invertible, right? Remember, we can write an MA process as an infinite autoregressive process. And what we want is that the coefficients get smaller. The coefficient of YT minus 2 is smaller than YT minus 1. The coefficient of YT minus 3 is smaller than the coefficient of YT minus 2. So that the most important variables are those in recent history. And that's called invertibility. And for that to be true, we need the theta parameter for the MA to be between plus and minus 1. Now, we're going to get a little bit mathematical and introduce the thing called the backshift operator. This is kind of baby steps, but when we get to put seasonality in, the only way to figure out what the model is doing is to use this so-called backshift operator B. So I've just written down equation 1 and equation 2 as exactly on the previous slide. And the backshift operator B is defined by, if you do backshift on Z of T, you get Z of T minus 1. If you do the backshift operator on Y of T, you get Y of T minus 1. So backshift says move the process back 1 point in time. Any question about the definition of a backshift operator?
Dr. Sridhar, this is Tathagata, remote
Yep.
today. Is backshift operator like a function which
it's a function. It's a function on you can think of it on a column. If we were doing linear algebra, this is a function on a column, right?
So it's a function acting on that vector zt, which is transforming the zt into zt minus 1. Okay.
Yep. So it turns out when we have seasonality and we have an ARMA piece for the regular piece and another ARMA piece for the seasonal piece, the only way to figure out exactly what the model is doing is to use this backshift operator. Okay? So we can rewrite, and again, the one thing about this is practice makes a beautiful thing. Once you've gotten practice with this, you'll go, wow, I should have been using this backshift operator years ago. So we're going to write equation 2 in terms of the backshift operator. And it looks weird, but let's actually do. Let's look at the left-hand side. 1 minus C1 of B of YT minus mu. So let's do that. Well, we're going to take the 1 piece and we're going to multiply that by YT minus mu. That's going to give us this piece. And then we're going to multiply the C1B by YT minus mu. And that's going to give us this piece here. Everybody good? So YT minus mu becomes YT minus mu. And then if we do the backshift operator on YT, that becomes YT minus 1. Right? That's all we did. We used the backshift operator. and the backshift operator on mu. Mu doesn't change with time, so mu stays at mu. So you see how this simple backshift operator gives us the left-hand side of equation 2. Now let's look at the right-hand side. The right-hand side is 1 times A of t, which is A of t, and theta 1b times A of t. So if you do b times A of t, you get an A of t minus 1 because we backshifted the A of t. So it's just a little bit of fun math algebra. You will see that if I'm going to fit a seasonal ARIMA 011011 is really popular for income series. We're going to fill a whole page with these little equations. But don't worry, we will figure it out. It's not that hard. Any questions about how the backshift operator works? It really doesn't add much value here, but it's just a way to learn in the simplest setting how it works. Any questions? Okay. So,
Sorry.
Again, yep, okay.
Sorry, Dr. Peter. Can you go back, please?
Yeah,
So,
sure.
yeah, just trying to follow here. So you said equation 2 is written in terms of the backshift operator, but just can you explain so what you did to equation 2 to get the 1 minus phi b yt minus u?
So here's what I did, subs. So what I used was experience to know that I can write this bit, right? I used experience and some rules, and I'm not going to explain the rules to you because we're going to get down in the weeds, and I don't want to get there.
Gotcha.
Okay?
Gotcha. Yeah.
Right.
Okay, I see. I
So
follow it. I follow it.
If you know, it's a great question, sir. If you let me just indulge me. So let me give you the big picture. So if I want to do AR1, I'm going to do 1 minus C1B. If I want to do AR2, I'm going to do 1 minus theta 1B. So let me say, misspoke. Excuse me. Let me start again. If I want to do AR1, that's 1 minus C1B. It turns out if I want to do AR2, it's 1 minus C1B minus C2B squared, etc., etc. So we're going to get some rules, but that's getting way too complicated at this point. So trust me. Are we good?
Yes. Thank you.
Okay. So again, I've written the top part down as our definition of ARMA 1.1. Now, it turns out it's a bunch of messy algebra that the autocorrelation function is given by this. It makes my brain hurt to look at it. 1 minus C1 theta 1 times C1 minus theta 1 over 1 plus theta squared minus 2 C1 theta 1. So that C1 doesn't really help you. It's a very complicated function of the AR coefficient C1 and the MA coefficient theta 1. Remember, if we had AR, the autocorrelation of lag 1 was just equal to theta 1. If we had MA, the autocorrelation function was MA1, the autocorrelation function was a step function, step down. So, if you have a time series that's ARMA 1.1, the ACF decays exponentially or is damped sinusoidal, and the PACF decays exponentially and is damped sinusoidal. There is no cutoff, right? No cutoff. Okay, my voice is coming in and out. Thank you for letting me know. Okay, so we have exponential decay in the ACF or damped sinusoidal in the ACF. We have exponential decay in the PACF or damped sinusoidal. So if you remember, when we had AR, the PACF cut off and that told us what order. When we had MA, the ACF cut off and told us what order. Here, we're out of luck. We're flat out of luck, as we say in Australia. Okay. It doesn't give us any information about what the order is. So again, I love to generate processes where we know the answer. So this is ARMA 1-1, and the C is 0.8, that's strong, and the theta is minus 0.8, that's also strong. Here's the time series. Here's the time series. It's a mixture of autoregressive and moving average. It's pretty clear that there's some autocorrelation going on. You see periods in the data. You see periods in the data where it's below the mean consistently. You see periods in the data elsewhere it's above the mean. But have a look at the ACF. The ACF is a set of stairs. The PACF is this damp sinusoidal. So that provides no information. How can you get that it's order 1 and order 1 out of that? You can't. So this is where life gets really tricky. So when I first learnt time series, we were flat out of luck. There wasn't actually a method in the 1970s to figure out what order to put for autoregressive and moving average. But subsequently there have been some methods which we're going to talk about tonight. So let's fit an ARMA 1-1 process. Here we have to know the truth to know what to fit. We're going to figure out how to do this from the data, and we're going to do that carefully in a series of steps. But to fit one is really easy. You just go to time series in JUMP, you put in P equals 1 and Q equals 1 and push go. And notice that we reproduce the parameters really well. So we get 0.786 for phi1, the estimate of phi1, and minus 0.797 for the estimate of theta1. So we do reproduce the truth pretty well. And here are our residuals. The residuals resemble white noise. So ARMA 1-1 is a valid model, which is not a surprise. Not a surprise because we know the process from which the data are generated. Any questions up until this point about what we've done? Okay, let's move on. So, here's a table that I love, right? If the ACF cuts off at lag Q, then it's an MA process of lag Q. If the PACF cuts off at lag P, then it's an AR process of lag P. For an ARMA PQ process, neither the ACF or the PACF provides direct information on P and Q. So we're flat out of luck. So what shall we do? If you've looked at the notes, you'll see what we can do. Anybody got any ideas? Use your statistical modeling prowess. What would you do? Big picture, general. Worry, absolutely. Well done, mate. Worry. Yep, that's the first part. Make yourself a cup of tea. That's the second part.
Would you fit one first and then the other?
Yes, you've got to try and print it. Well done. You've got to try and separate the two pieces, haven't you? You've got to try and separate the AR piece and the MA piece. Good. Good. That's a good idea. So one idea behind one approach to choosing the process. Now, we're going to think in the ideal world here. We're just going to assume that we know stuff that we don't in practice. And then we're going to figure out what do we do when we don't know the stuff in practice. So let's imagine that we know that it is, or we suspect it is, ARMA 1-1. So the AR order is 1, the MA order is 1. Then what we're going to do is we're going to write the left-hand side of this equation as Z of T. So Z of T is like an AR piece. This part here is if we knew the right-hand side, if we knew theta 1, then we can produce an MA process. So if we knew theta 1, excuse me, I'm misspeaking. If C1 was known, then we can calculate ZT, and we have an MA process. So if we by chance know that it is AR1, that piece, then we can look at the ACF of the Z piece to figure out what order of MA that is. Okay? So let's actually do that. So this is the idealistic approach where the statistical higher being would send us an email or a text saying, excuse me, Dr. Shiva, I'm going to tell you that the AR part is order 1. So I'm going to calculate Z of T as Y of T minus mu, etc., and I'm going to know from the statistical higher being that the mean is 0 and T1 is 0.8. Then if you look at the series ZT, have a look what happens to the ACF and the PACF. The ACF cuts off. The ACF cuts off at lag 1. So that says, excuse me, this looks like MA1, and the PACF is damp sinusoidal. So if we knew what the AR piece was, we could subtract that out of the process and then use what's left over and model that as MA and figure out the MA order. Okay, but life is not so easy. We're going to look at unemployment data later on, and we won't know what the AR piece is. So, if we keep going with the idealistic approach and we fit an MA process to the Z's, yep, guess what? We get something that does really well. We reproduce the mu equals 0, and we reproduce the theta 1 as something very close to minus 0.8. So in this idealistic approach, if we can figure out what the AR order is and subtract that out of the process, we can then use the altered process to figure out what the MA order is. Any questions about what we've done on these couple of slides?
You might have to repeat it, Dr. Sheila.
Okay.
It went quite fast.
Okay. All
Yeah,
right. You just slow me down, sir. You just slow me down. So again, I've started with equation 2, which is our vanilla flavored equation for a AR1 MA1.
Mm-hmm.
The AR1 part has the phi1 YT minus 1. The MA1 part has the theta 1 times AT minus 1. Now, if I could figure out, Tapagata, if I knew what the phi1 and the mu were, I could subtract them from Y and get a thing called Z, right? And the Z is the left-hand side of equation 2. And so I have ZT equals AT minus theta 1 AT minus 1. That's just the moving average process from last week and the homework you did. Are we good with that?
Mm-hmm.
Are we good with that? Any question about that?
Yeah, I'm good.
Okay, good. And then, so that's what I did. I calculated ZT by subtracting mu and C1 YT minus mu from the YT. And I assumed the true values of mu and C1, which is idealistic and unrealistic. And look at the time series ACF, cuts off at lag 1. The ACF goes on, that says this is an MA1. So if I fit an MA1 to disease, I end up getting an MA1 with coefficient very close to minus 0.8. So what I've done, Tapagata, is demonstrate to you that if I can figure out the AR piece and subtract that off from the Y, I can then use what's results to figure out what order the MA piece is. Are we good, sir?
So you're decomposing it into two processes.
Yeah, two pieces, exactly.
Okay.
Yes. Good. So, let's go and be realistic now. So we have what we did before, but we're not going to subtract from the z's the actual value of mu and the actual value of P1. We're going to subtract off estimates of them. Estimates of them. Okay? We're going to subtract off estimates of them. Because with this unemployment data, we have no clue what any of the parameters are. So the second part of the idea is to ignore the MA process in equation 2 and just fit an AR1 process. So just look at this. Just assume the world is this and ignore the MA1 part.
Mm-hmm.
It's, not the best, but we got to start somewhere. Okay?
Question, Dr. Sheeter?
Yep.
So for the first part, we said that assume we know the AR piece. Here we're saying ignore the MA piece. Why would we not assume we know the MA piece?
Well, you could do that, and I could show you that's going to work. But sometimes, mate, we're going to have to face up to the fact that we don't know either piece, mate.
Okay.
Right?
All right.
Okay. Are we good?
So then, by extension, could we also have ignored the AR piece for the first part?
Well, it turns out that doing this is going to be it's easier to do this, the AR part first and then the MA, right?
Okay.
I'm just doing baby steps. We're going to get to what people did in the 1980s, okay?
Yes, thanks.
So, I'm going to fit an AR1 model to the ARMA11 model, right? So that's saying I'm just going to ignore this term that I crossed out. I'm just going to assume that this is really AR1. Now, have a look at the AR1 coefficient here. The AR1 coefficient should be about 0.8. It's 0.89 with the standard error of 0.01. Wow. So we got close, right? 8.9 plus or minus 2 standard errors is plus or minus about 0.03. So we think that the C1 is somewhere between 0.86 and 0.92. So we're a little bit off. We're kind of in the ballpark. We're a little bit off. Okay. Now, if we look at the residuals, what's left over, right? What's left over? What process do you see in the ACF and the PACF? In the PACF, this goes on for many lags, doesn't it? Yes? But it cuts off here at lag 3. Oops, lag 3. Everybody good with that?
Yes.
So the PACF damps on your soil. The ACF of the residuals cuts off at lag 3, so that says the residuals look like MA3.
Yeah.
Yes? So we're going to say as our first guess, and not our last, we're going to fit an ARMA 1-3. So let's step back. Why is that? Why are we doing that? Well, yep, well done. Well done. That's it.
So one question. Did we really prove that the AAR was 1?
No, we haven't. We just started there. But imagine we could iterate through all this, couldn't we?
Okay.
Yes? We're still doing baby steps, sir. Yes?
Okay, good.
But you see how if I pick one, I can work out the other, can't I?
Yes, correct.
Good. We're going great tonight. We're going great. All right. Let's look at the ARMA 1-3, and then look what happened. Look at the coefficients of MA2 and MA3. right? The coefficients of MA1 and it is significant. The AR1 is significant. These other two. So this suggests that we fit an ARMA 1-1 model, which we already did. So you get kind of an idea. We pick one side, calculate the residuals, and then fit the other. Everybody good with that idea? It's not bad, is it?
So what did you, when you fit this model, you obviously see that the MA2 and MA3 estimates are insignificant.
Yes.
Not significant. That means you revert back to your original hypothesis that it was AR1, MA1.
Yep. And then if you go back to slide 9, we already fit that, found that's a valid model.
Right.
Okay? So this all depends on, you know, making guesses for the AR part and then estimating the MA part, doesn't it?
Hmm.
Yes? That's what we did, isn't it? Okay.
So in doing all this, are you watching out for the SBC is going down or not?
Am I watching out for what, sir? Sorry?
The SBC is going...
We're going to get to SBC. We haven't looked at that. This is a visual thing, okay? This is a visual thing. We're going to do SBC later in this class.
Consider a question. Right now, you did only AR1. Should you also test AR2?
Yeah. So, in theory, the AGO, if I had infinite resources, I could fit all the models, AR1, AR2, AR3, and then do it, right? Yes.
Yeah, but I was thinking only fitting the next step just to see if you get a better model or not. Otherwise, you stop.
Yeah, you can do that. So you can think up all your ways. I'm going to make you guys graduate students at the University of Chicago in the late 70s and early 80s. And I'm going to show you what they decided about how to do this, okay?
Okay, thank you.
But remember then, sir, the computing power was slow. So if you say, I want you to fit 3 of these and 6 of those, so that's 18, they're going, no, that's not going to work. Okay. Then if we actually look at SBC and AIC, the ARMA 1-1 model is clearly better for SBC because ARMA 1-3 has some statistically insignificant terms. All right. Now, here's where we go. Rui Say and George Chow, 1984 Journal of the American Statistical Association. This is a classic article that, you know, when I look at this every year, I genuflect about how smart these guys were and are. Rui Say still teaches at the University of Chicago. I think George Chow is retired. So this is the extended sample autocorrelation function. And what they do is, as we'll see, is effectively an iterated version of what I just showed you. I showed you just one step. Okay? Now, guys, I'm going to show you a rule about how to look at this extended sample autocorrelation function. We're going to look at triangles. So if you're not a math person and you don't get excited by equations, don't worry. It's not important. What I need you to be able to do is look at this ES, ACF and interpret it. But my experience of having taught this for the 3rd time to the analytics students is some of you get really excited by a few math equations, and so I've tried to write those down. I'm not going to go through every one line by line, but I believe I have put enough of the derivation that you can figure out what it is that how this works. So they take exactly what we did. They take the Z hat T series, with the phi hat 1, and they use iterated estimates which are consistent. Consistent means they're correct even if the model fitted is not correct. And then they get this thing called the extended sample autocorrelation function. When the true model is ARMA 1-1, then the ES-ACF is expected to cut off at lag 1, after lag 1. Now, if you're doing this not 1-1 but PQ, you have to be able to estimate phi hat 1, phi hat 2 up to phi hat P. It just becomes more complicated. Imagine, Diego, what we would do is we would say, let's suppose it's AR1, we do those, we adjust as if it's AR1, let's assume it's AR2, let's adjust everything assuming it's AR2 and look at the MA piece, and we go up to P. And you'll see that SAS typically does this up to P equals 5, unless you tell it something else. And so basically what this is doing is saying, I'm going to adjust out the AR piece and then I'm going to look at the MA piece. And then I'm going to be able to say, look at both together. So here's an example. If you have a look at this triangle, what we're trying to do here, is look at a corner where all the p-values are non-significant. All the p-values are non-significant. Right? All the p-values are non-significant. So this is the AR are the rows, that's AR row 1. The MA is the column, that's MA 2. So what we're going to do is we're going to ask SAS to give us this extended sample autocorrelation function, which is based on these calculations like I showed you. Assume it's AR0, that's the top row, fit all the MAs. Assume it's AR1, fit all the MAs. Assume it's AR2, fit all the MAs. Assume it's AR3, fit all the MAs. Okay? So we're looking for a triangle of zeros with a vertex at P, the AR order, and Q, the MA order. So let's go back to our trusted example. Remember, we know it's ARMA 1-1. So we say, please give us the extended sample autocorrelation function. Now notice here, this is real simple. When you do the proc-arima, you just say identify, which tells you what the Y variable is. It's YT, and then you type in ESACF. You don't even have to tell it what model you see. Okay? Then it comes back with the values of the autocorrelation function, but you actually interpret the p-value. So we're looking for a triangle where the p-values are not significant. So I'm not a very good drawer with a mouse, but if you look, there's a triangle, right? And what have we got? We've got AR equal to 1 and MA equal to 1. So this tells us, based on this extended sample autocorrelation function, that it is ARMA 1-1. So let's do this in 2 levels. A question about how do you actually figure out what triangle to use. Does anybody have a question to figure out what triangle to use? Are you clear what we're looking for in terms of just the triangle before we get into the theory of it?
Dr. here, I got it. I mean, I think I understand how you pick the triangle, but I wanted to understand why, for example, you pick an AR1, MA1 instead of just a pure AR process, for example, with MA0, so which will be just AR process.
Well, again, here's the deal. All of these other things are highly statistically significant. So this method says, look for a triangle where all of the numbers in the triangle are statistically insignificant p-values, all large p-values. And here, because we generated the data from a pure ARMA 1-1 process, there's the triangle, right? It works perfectly. With sample data, it doesn't always work this well. But here the rule is very clear, right? The rule is very clear. Yep, there's 2 things. can we do the rule? And then why does the rule work? Let's focus on can we do the rule. Any questions about how can we do the rule? Okay?
Yes, one question, please.
Yeah.
So does it mean this could as well be an AR2 MA3 model, for example?
AR2.
MA3, yeah, since it's within the
MA3.
triangle. Yeah.
Yeah, but again, if I do that, there are all of these statistically non-significant ones above it. I don't like that, right? So let's do your theory, sir. Is it Marek?
Yeah.
So Marek, tell me what your theory is. You think it's AR2 and MA3, right?
Yeah.
So I go here and I draw a triangle, and I go, I got a problem, Houston, because look at these things here are not statistically significant, and they're outside my triangle.
Okay.
Yes?
Yep.
That's not a good choice, is it?
Sure.
So we're looking for a triangle where everything outside of it is statistically significant and everything inside of it is statistically insignificant.
Okay, thank you.
So Dr.
weird.
Sheeter, I'm
Yeah.
sorry, I just want to understand the rule. So we pick the triangle, and then the model that we select is the one that is on the vertex of that triangle?
Yeah.
On the corner?
Exactly, sir. Exactly. And where's the
Okay.
vertex? It's that row 1, column 1, right?
Okay, got it.
AR1. Yeah, it's a beautiful thing, isn't it?
Okay.
Yes?
So Dr. Sheeler, there won't be anything significant within that triangle then, ever?
Well, no, I'm going to show you a process. Well, the good, bad, and the ugly, sir. It doesn't always work. It's like life. You know, here we don't have any outliers. We don't have any level shifts. Now, you put some of that stuff in there, and this thing is not that crystal clear. Okay? But it's a good tool that sometimes really helps us out. All right?
Dr. Sheeter, this is Gracia. So
Yes, Rachel.
to understand this triangle, what about the values like an AR4 or an AR4 MA1 or AR3 MA2 where would be outside of that triangle?
Okay, so we're gonna let's take the Gracia way of doing this. All right? Tell me what you'd like. You want AR3, right?
No, I don't.
Yep.
No, the question is, if we draw the triangle like as you suggested, starting with the AR1, MA1,
Yep.
and then we come down, right, there's going to be values that AR4 is going to be outside of the triangle and it's statistically significant.
Yeah, that can happen. So you'll see that SAS gives you the top 3 answers. It's possible for things in the triangle to be insignificant. It's possible for things outside the triangle to be not significant. So there you go. The world is good, bad, and ugly, Christian.
So we're just looking for a majority, I guess, is the rule.
Majority, yeah.
Okay,
Yeah,
thank you.
I'm going to show you an example where I still scratch my head. Right? I can't fathom why SAS picked what it did.
Thank you, Dr. Sheeter.
Right. But it's just a tool for us. Now here it's very clear, isn't it? Look at all the terms outside of the triangle. They're all statistically significant. So I would bet, you know, a week's pay on the fact that ARMA 1.1 is going to be a pretty good model. Now, if you have what you just said, Gresham, lots of stuff inside and outside the triangle, I go, well, it's telling me ARMA 1.1, but I'm not very convinced. Okay? Good. Now, in terms of the math, what I'd like you to do is, you can get into the weeds if you want, is just think that all these guys did was figure out a smart way to iteratively fit the AR piece, subtract that off, figure out fit the MA piece to the residuals, and keep doing that over and over. So they could do it quickly. And then they summarize things with the autocorrelations. Okay. And look, yes, there we go. SAS found order 1.1. Now, here's something I know we're going to have a big bunch of back and forth about. We do every year. It says P plus D. What does P plus D mean? And we're going to talk about this again next week. So I'm going to jump in the deep end of the swimming pool with my hands tied behind my back. What does P plus D mean here?
Does it mean a process of AR process of order 1 with a difference?
Yep. So what you have to do is this tells you here we have done no differencing, right? The data is the data, so we know D equals 0. So this is telling us that P equals 1. All right? If we had have done a difference, D equals 1, this is telling us that P equals 0. If it's D equals 1, this is telling us that then P equals 0. So I'm not going to do differences. They're called ARIMA models, and I'm going to do those next week. But I'm just warming up the water so that we don't get freaked out when we see this P plus D next week. Okay? Here there's no differencing, so D equals 0, so we know P equals 1. Everybody good with that? Simple equation, right? So we know D equals 0, so we know this is our situation. D equals 1. All right, let's move on. Now, these same people a year later came up with a scan statistic. It's completely different. It turns out if you talk to some of the time series people, there's some who say, no, ESACS, terrible, scan is great, and others who say scan is terrible and ESACS is great. So, look, I'm a pragmatic guy. I'm going to tell you what the literature says. And so what they did was use the multivariate approach. So remember in multivariate analysis with Dr. Dabney, you talked about eigenvalues. Eigenvalues tell you the structure in the data. How many significant variables are there in the data set? And you can use the same idea to figure out what the order P and the order Q is. And I'm not going to show you anything more. I've got the reference there because the mathematics of this is PhD level math stuff. But the great news is to use this in practice. So unlike the ESACF, which I can explain in general to you, the scan statistic I can't. It's too complicated. But its use is really even easier than ESACF. What we're looking for is not a triangle, but a rectangle. We're looking for a rectangle. So we're looking for a pair of values, again the vertex, where everything outside the rectangle is statistically significant and everything inside the rectangle is insignificant. Let's look at what happens with our generated example. Again, all we do is put in scan. Okay, let's go to the probability values. Where is our rectangle? Where is our rectangle where all the values inside the rectangle are statistically insignificant and everything outside the rectangle is statistically significant? It's actually much easier to draw and find a rectangle in my experience. And so guess what it does? This says that the upper vertex is armor 1, 1. Right? This says armor 1, 1. Everybody good with that? Everybody understand how to just look for a rectangle? Everything inside the rectangle graph should be insignificant. High p-value, everything outside the rectangle should be statistically significant. And it doesn't always work like that. We'll look at a real example shortly. But it turns out in my experience, the scan thing is easier to look at than the triangle. Any
Dr.
questions?
Sheeta, yes, I have a question. Can you go back a couple slides?
Yeah.
Right there. What does the word maximal mean in the blue text? The top left-hand corner of the maximal rectangle pattern?
Yeah, maximal means the biggest.
Oh, okay.
Biggest.
Okay.
Right? So it's just a fancy word, biggest.
All right. Gotcha. Thank you.
Yep. Nice question. Thank you. And so, guess what? It finds 1-1, just like we did. So, you can imagine there's been a lot of controversy, and now there's this famous study from 2008 and found if you look at simulated AR, MA, or ARMU, my bad, that should be ARMA, typo, sorry, ARMA models, SCAN performs better for identifying ARMA. Let's think about it. What SCAN does is look at eigenvalues for the whole matrix. It doesn't, it tries to find the AR and the MA pieces together. The ESACF, it partials out the AR part, and it turns out to work really well at finding the MA piece. Right? If you think about the whole motivation for this extended sample autocorrelation function, yeah, again, that should be ESACF, my fat finger typing. You remove the AR piece and the MA piece is revealed. So it's not surprising that that does well. And then SCAN does better if you just have AR model. So the whole 9 yards here is we're just trying to find trial models we can fit. And we're not going to ever take just one model. We're going to see that we're going to, in fact, for this example with unemployment, we're going to look at 6. I typically always look at least 3 models. Okay. So, fast forward to the 2000s. That was the 1980s when there was no such thing as a fast laptop like you guys had. You know, the biggest computer you could find was slower than what you carry in your briefcase. So what people do now is to use an information-based criterion and fit many, many models. Let's fit every model up to this order for AR and up to another order for MA, and let's order those models in terms of AIC or BIC. Now, in time series, people typically call BIC SBC, after the fellow Schwartz who wrote the original article. They're exactly the same thing. Schwartz's Bayesian information criterion. Now, remember from 608, the BIC penalty is stronger. Now, if you want to find a parsimonious model, that is, if you want to get ARMA 1-1 when it is ARMA 1-1, then you should use SBC. If you don't care about interpreting the model and you're just interested in having the lowest prediction error, then AIC is generally preferred. So remember from 608, if I have a large data set and the models I'm considering include the true model, the true model is ARMA PQ for some P and some Q, SBC will find the correct P and the correct Q. Alternatively, if I want the best predictions and I have a large data set, AIC will come up with predictions that are indistinguishable from those if I knew what the correct P and the correct Q was. Now, we have to be really careful about worrying about overfitting. Remember, we're using information criterion because there's a penalty function. There is a penalty function. So it is crazy to use MAPE and MAIM, mean absolute prediction error, mean absolute error, or median absolute prediction error and median absolute error should not be used unless you're computing them on a validation set, which we shall do later in the semester. Okay. So there's a great thing in JUMP which doesn't exist in SAS in a straightforward way, called a REMA model group, and it fits every model over a range of values. And much to my chagrin, so much to my displeasure, as we say in regular English, what JUMP does is order the models from best to worst in terms of AIC, not SBC. And the young people have heard me my displeasure at that many times, but they still do it. So, if you have a time series model for Y of t, you can go to a thing called a Riemann model group, the option, and here I'm going to do a very small number of models. I'm going to limit t equals to 2. So it's going to fit every ARMA model with t equals 0, t equals 1, t equals 2, and every combination with MA equals 0, 1, and 2. And here's the deal. You can put 10 and 10 or huge numbers here, but please don't do that. You'll see with experience that you want to try and use some idea, get some idea of the maximum order out of the ESACF, the scan, the autocorrelation, the partial autocorrelations, and limit the number of these models. Because after the midterm, there is a whole box of stuff that we're going to start looking at, is because there's the seasonal part, right? This tells you, the seasonal part says, if it's monthly data, what happened last September. So we're going to have the ARIMA part, which is what happened last month, with the seasonal part, which is what happened 12 months ago. So you can get this completely out of control if you make those numbers way too big when you're doing the ARIMA and the seasonal ARIMA part. Anyway, we will get right into stuff. Yes.
On that dialog box, why does it say total number of models 9?
Because 0, 1, 2 is 3, sir. 0, 1, 2 is 3. 3 times 3 is 9.
I see.
Yep. Write a matrix for me.
Yeah, that
are the rows, right? Row
right, that,
0, row 1, row 2, column
gotcha.
0, column 1, column 2. Are we good?
Gotcha. Thank you.
Yeah, 2's the max. Yep.
Dr.
That's what
Sheeter,
telling us. Yes.
I have a question based on the few slides ago. You mentioned don't use mean absolute error or mean absolute percentile error unless we have a validation set. So
Yes.
my question, with traditional regression, you recommended like a 70-30 split.
Yep.
Is there a general rule of thumb of what is the right size of the holdout test set for this time series?
That's still a good That's still a good rule. That's still a good rule.
70-30.
Yep.
Thank you.
We will look at a whole week of looking at validation sets, but we're still learning to build models, sir. Right? It's like we're in elementary school. We can't play with the big kids yet.
Okay.
Okay.
Dr. Sheeter,
Okay. Here's what happened. So it fitted every model. And look, it ordered them from the lowest value of AIC down. The lowest value of AIC is 28,846.
Dr. Sheeter, what is AR0, MA0 model? What is it?
Yeah, that's a Riemann 0. 0 is saying that there's no autocorrelation in the data.
Okay.
Right? You just need a regression model, sir. Right? There's no autocorrelation. So it's not surprising it gets killed, right?
Yeah.
So it also does weights based on the AIC. So it does weights based on the AIC, and I find these completely useless because I don't look at AIC, I look at SBC, and you'll see as soon as this week when you look at the homework why AIC tends to overfit models. You get too many AR terms and too many MA terms that are not significant. So if you want to try and explain the model to you, you've got no chance at all. But here, because it's small, we chose only to go up to order 2 on both. The AIC order is the same as the SBC order. But the ARMA 1.1 model is selected as best. So this is really good. it says if we use the ARIMA model group, we select the correct model, ARMA 1.1. If we use EFACF, the extended sample autocorrelation function, it says we're going to choose the best model, ARMA 1.1. If we use the scan statistic, it says we're going to choose the best model as ARMA 1.1. So it's really not that surprising that we do well here because we generated the data from a pure ARMA 1.1 process. Okay? So let's, yep. The weights are to do with the value of AIC. You can look up the manual. Because I don't use them, I don't look at them. So the only thing I'm going to look at here is this column called SPC. In my statistical religion, if you want to find a parsimonious model, look at SPC and ignore all the rest. Okay? And if you look in, yeah. And then the other thing you'll see is, notice that the first model has a much lower SPC, 2861 versus 2868. There's a jump of 7 there. So it's saying that the SPC of ARMA 1.1 is a bunch lower than that of ARMA 1.2 and ARMA 2.1. But again, this is a great experience thing. All right.
Question?
Yeah, question.
So, Dr. Shearer, you mentioned that using the 3 different methods that you proposed, the triangle, the square, and this one. I'm
yes.
sorry, I just forgot the names. So yes. For these 3 methods, we got the same answer.
Yeah, that's not surprising because we use...
Yeah, because the data is synthetically generated. Yeah, I got that.
Yeah.
My question is, are there some cases where the methods give you different answers? And if so, which of them should you trust more?
That's exactly what we do next, Alejandro. All the methods give me a different answer on the next example.
I'm sorry, my bad. Okay, keep going.
Okay, so let's take a short break because my brain hurts. I'm sure yours does. Let's take a 10-minute break, and we'll see you at 10 after the hour. Okay, thank you.
Dr. Shearer?
Yep.
I had one more question on this topic.
Yeah.
So if we test and validate, do we still look at the SPC or do we look at the error, or can you choose either?
So we're going to use the SPC to pick which models we should concentrate on first. We typically feed the best 2 or 3. And then we've still got to look at the residuals to see if it's a valid model. Okay?
Okay. Yep. Thanks.
Good. All right. See you back soon. All right. Let's continue. Is everybody back? Good. All right. Let's move on to a real example. Monthly unemployment rate. There is much interest in this country and essentially every country in the world with unemployment rate. And we're going to look at seasonally adjusted unemployment rates because that's the one that's usually reported. Because if you think about the seasonality, think about the college graduates and the high school graduates that come onto the market. They're going to clearly affect the unemployment rate. So what is reported nationally is a seasonally adjusted unemployment rate. Now, we don't know how to do seasonal adjustments yet, but we will learn that. And what we want to be able to do is to take from 1990 up until February 2017 in order to predict the next few. So that first thing is that's not correct. If we're going to go predict March, if we're going to predict May, etc., then clearly we're going to go from 1990 January until April 2017. Another typo. So here's my challenge, because every year I update the class note and I try and use the most up-to-date data. But my bad, that should be April. So you can see here is the Bureau of Labor Statistics. Here's a graph of the data. You can see that unemployment went up for a while and then down. The series is clearly not stationary. So we're going to look at change in unemployment rate because we don't know how to use differencing yet with AR and MA put together. We're going to talk about that next week. And notice that I have hidden the last 4 rows of the data. Okay. Step number 1, have a look at a time series plot. What do we see from the time series plot? What features can you see? Help me out.
The points tend to be above the line and below the line. And they
Yep,
persist
there's
there.
certainly some autocorrelation, Fiona. Thank you.
There is probably additive outliers about January of 2009.
Yep. January
Potential
2009. Well,
level
these 2
shift.
points, 2011. Look at that baby and this one. Is there a level shift in here?
Yeah,
Yes.
looks like.
This looks like a kind of an outlier here. Yes. Maybe this one here. Yes.
Mm-hmm.
Now, let's look at the PACF and the ACF. We have significant stuff down to about level 6. Maybe 7 is marginal. And then here it's about down to level 6, lag 6. Yes? But do you see, does the ACF cut off or the PCA-ACF cut off? No. So this is saying to me, excuse me, JT, it's popping out of my porridge that this is probably ARMA, right? Because it doesn't follow the AR process, which says the PACF cuts off. It doesn't follow the MA process, which says the AR cuts off. So I've found everything you did, additive outliers and a possible level shift, and I think this is potentially ARMA. Okay? Everybody happy with that decision?
Dr. Shida, I have a question.
Yeah.
Do you have to adjust for the additive outliers and level shift before you make that conclusion that it's ARMA, or you can do that straight from this?
Well, ideally, this is an unsolved research problem, Tapagato.
Oh.
It would be much better to have adjusted for these outliers before we look at this PACF and ACF, because we know that they affect those ACFs and PACFs, don't they?
Right.
Yep. That's
so
a
you
good
can
point.
Conclude, so basically, based on this, you can conclude that this is an ARMA model, even if you haven't fixed.
Yeah, you hope.
Okay.
You hope,
Okay.
sir. But yes,
you make that assumption.
it's pretty clear here. It's pretty clear here that this is not AR, this is not MA. Our best hope is put them both together.
The other question I had was previously when we started with ARMA, we were expecting to see damped sinusoidal as well, but I don't see that here, at least for the autocorrelation.
Right. Again, I use this example because this is realistic, you know. Those other things are ideal worlds. We don't really see that, right?
Okay.
Yes? Yeah. No, I'm not understanding you, Sam. Help me out more slowly, please. What do you see? Again, I'm not understanding you, Sam. Can you help me out here? Okay, all right. Thank you. So I'm going to fit. Now, here's the first choice I have to make, and I'm going to be very conservative because we just started here. I'm going to use a rule which is conservative. I'm going to say I'm going to look for lags up to AR6 and MA6. Why did I pick 6? I picked 6 because lag 6 pops out of my porridge in the PACF and the ACF. It turns out that that is being conservative. It's probably taken too many lags, but we'll see. So we have to come up with a starting rule. Everybody good with that? Now, let's look at the scan statistic. Let's look at the scan statistic. This is the bottom right. So where is our rectangle? Where is our rectangle? What do you think?
ARMA 1-1.
ARMA 1-1, yeah.
Yeah, it's pretty obvious, isn't it?
Yeah, it's ARMA 1-1.
Good, we did great. ARMA 1-1. And the only thing that kind of is a bit of a snafu, Drescher, is this point here, right?
Yeah.
Yes,
Otherwise,
sir.
it follows all the rules, doesn't it?
Yes, sir.
Okay, now, here's the real tricky one. We're looking for a triangle over here. What do we think?
Also ARMA 1-1.
That looks like 1-1 as well, if I'd be
Yeah.
guessing.
It's the same.
Okay, so you think it's ARMA 1-1.
Mm-hmm.
There's a lot of stuff that's insignificant outside this box, outside
Yeah.
this triangle, right?
Yeah,
Yeah.
true. That's true.
It's much less convincing, isn't it?
Yeah.
Yeah, it is.
Yes? Nothing pops out of my porridge there, right?
No porridge popping there, no porridge.
No porridge popping there, JT. So let's
Nope.
see what SAS did. SAS said scan was 1-1. Okay, we get 10 out of 10. It said ESACF was 3-3. Shoot me now, JT. Shoot me now. Don't torture me, mate. Just shoot me. That's not very convincing either, is it?
No, that makes no sense to me. It's popping
Right.
into the porridge, not out of the porridge.
Yeah. So I think 1-1 looks best, but whatever algorithm SAS is using, it thinks 3-3. So all is not lost here. It just says the ESACF is pretty confused, is what I would say. There's nothing that strongly pops out of the ESACF. Yes?
Mm-hmm.
Dr. Scherer, what is the meaning of the other values behind below? Are they alternative optimum?
They're the next one. Let's look at scan. Let's look at scan. After 1-1, right, let's tick
6-0.
6-0. Right? If you do 6-0, they're all insignificant, aren't they?
Yeah.
Yes?
Yep.
So it lists them in the order it thinks is best. Okay, Diego?
Okay, thank you.
Now, on the midterm tests, we're going to do a review next week. You'll see that I give you some data sets and you have to pick from the ESACF and the scan statistic what model. I will never give you one like the scan statistic in this example because it's not clear. But again, all is not lost. It's just saying the scan statistic doesn't have a really clear thought on what is best. Everybody happy with that logic? Whereas scan is saying, I really like 1-1. Everybody happy with that logic too?
Yep.
But isn't scan as easy to see? I think it's easier to look at rectangle than it is triangle. Okay. Now I'm going to do a REMA model group. I'm going to do up to order 6 for the AR part, up to order 6 for the MA part. SUD 7 times 7, sir, is 49, right? So we're going to do 49 models.
Yes, sir.
Are we good? Here we go. We push go. There's our 49 models. And have a look at what AIC says. AIC says 5, order 5-2. Please shoot me now. Put me out of my misery. I'm not going to fit AR5. Right? AR5. So this is a classic example where AIC wants to fit high order because it's chasing better predictions. It doesn't care about parsimony. It's happy to put in parameters that are not statistically significant. Now, what happened here? the mean absolute percentage error. It didn't print any of the values. Well, we got a problem, Houston. What happened? Well, nearly more than a quarter of the data are zero. You can't do percentage change when you divide the bottom by zero. So it doesn't do percentage error. Again, we're going to live or die by the SBC. So there's a great thing you can do in Jump. Click on anywhere in the data, click on columns, ask for the AIC rank and the SBC rank, and they will be added to the data. So if you look, the model that's ranked 1 in AIC is ranked 9 by SBC. The model that's ranked 1 by SBC is ranked 11 by AIC. So the first thing you learn is that these AIC and SBC information criteria, they chase different masters. And so they can give very different answers, very different answers. So what I would like to do is order by SBC. I want the models from best to last, first to last, and again, right-click anywhere on the data, sort by columns, select SBC rank, and check ascending. And here we go. Look at this. Rank 1, 2, 3 for SBC was rank 11, 19, and 5 for AIC. So what did it pick? It picked ARMA 1, 2, and ARMA 2, 1. And the SBC values are kind of close. 327, 325. They're kind of close. So, welcome to the real world. It chose very different models. The first model chosen by Scan was ARMA 1-1, which was ranked 6 in terms of SBC. The second model chosen by, well, the first model chosen by ESACF is ARMA 3-3, and that's ranked 12. And then the second model chosen by Scan, which was AR6, ARMA 6-0 is ranked 16. And then ARMA 4-3, ESACF, that's ranked 25. And again, I choose this example because I want to show you something that we all know and love, unemployment rates, and give you a realistic example. And it's all going to have a happy ending by the end of the deck. Any questions about this, what we're looking at in this chart? Okay, let's move on. So, you can really easily fit models by just clicking the box under Report and under Graph. So we're going to start by fitting the ARMA 1-2 model, and all you have to do is click Report and click Graph, and magic, it fits the model and gives you this plot. So it thinks that ARMA, the AR coefficient is very highly statistically significant. The AR1, the MA1 is very highly statistically significant. The MA2 coefficient is highly statistically significant. The intercept is not, and as we say, I don't care about intercepts. I'm just going to leave it in there for the moment. Now, the big question is it a valid model? And the answer is it a valid model? Yes! Have a party. Yes, absolutely. Yes. Valid model. Why is it a valid model? Constant variance, right? The residuals are consistent with white noise, yes? Now, in the residuals, do you see any outliers?
Yes.
Yes.
Good. We're getting good at spotting these, aren't we? Do you see any level shifts?
Yes.
Yes, probably about here somewhere, right?
Yeah.
Okay. Good. Let's look at the model chosen by Scan, the one we love. Remember, it was 1-1, right? So the model is is ignoring the intercept is parsimonious. The AR coefficient is statistically significant. The MA coefficient is statistically significant. Is it valid? No. Not a valid model. Why is it not a valid model? The residuals still have autocorrelation in them, don't they? There is.
Residuals grouped together.
Yeah, the residuals are grouped together. They don't look random. 7 of the lags have statistically significant autocorrelation.
Yeah, even partial.
7 out of 25 is more than 25%. That's not a valid model. Okay, sorry, scan statistic. You didn't do very well, sir. Right? Okay. Let's look at the ARMA 3.3. The ARMA 3.3 is a parsimonious model apart from the intercept. Everything statistically significant. Yes? And then, is it a valid model? Is it a valid model?
Yes.
Yeah.
Yes.
Although
Does it look
24th
like it
lag,
has outliers?
it does have. But Dr. Sridhar, 24th lag, we have some.
Yeah, but it's not. Its
article.
p-value is 0.13.
That's not statistically significant.
Not
Right.
statistically significant, okay?
Right.
All right, good. Now, let's go to the ones that are second best. We did ARMA 1.2 for the lowest SBC. Here's ARMA 2.1. And ARMA 2.1 is parsimonious apart from the intercept. Is it valid? Is it valid?
Yeah.
Yes.
Yes.
Good. And the outliers really stand out here, don't they?
Yeah.
Yeah.
Yes? There's a bit of a level shift up here and a level shift back down there. Okay, AR6, right? That was the second model chosen by SCAN. Is the model parsimonious?
No.
No.
No, because it's got an AR1 lag that's not significant. It's got an AR4 lag that's not significant. Is the model valid? Is the model valid?
Yeah.
Yeah.
The model is valid, but it's not parsimonious. Okay, good. And the final one is the second model chosen by ESACF is ARMA 4.3.
Here one.
Is it parsimonious?
No.
No.
Not parsimonious. Is it valid?
Yes.
Yes.
Yeah.
It is valid. All right, so let's summarize in the table. So let me be clear. I could have refit everything without an intercept. I'm old-fashioned. The intercept makes everything more stable. I'm just leaving it in. It won't change anything because it's common to all models. So we can say ARMA 1.1. We are not going to go any further with that because it's not valid. Is everybody happy with my decision? Yes?
Yeah.
Which 2 models would you fit if you had to go forward? If I allowed you to fit 2 models, which 2 would you pick and why?
First and
Those
second.
two.
ARMA 1.2, ARMA 2.1.
Why would you pick ARMA 1.2 and ARMA 2.1?
Parsimonious and valid.
Because they have the lowest
lowest
values
SBC values.
Yes, the lowest SBC values. Yes?
Mhm.
Everybody good with that?
Good with that.
Good with that. So what we're going to do is we're going to fit those 2 models and look for outliers and level shifts. Now, to be fair to SCAN and ESACF, we will see across the semester, sometimes they do really nicely. So I'm not doing this to trash them. It just worked out in this case they didn't do so well. Okay, so we're going to do ARMA 2.1. Now, I didn't see that many outliers, so we're going to do ARMA 1, 2. So notice here in the code, I have P equals 1 and Q equals 2, and I'm using this SAS file. This is a SAS file, and what I've done is make sure I have missing values for the last few time points. Because as we talked about in the online office hours, that automatically makes the additive outlier variables and the lever shift variables the right length. Otherwise, you won't be able to do forecasts. All right, let's see what happens. Let's look at the parameter estimates. The intercept is -0.005, good. MA1 is 0.963, good. MA2 is -0.206, good. AR1 is 0.925, something, good. And if you look at SBC, -327.286, -327.286. So the two things agree, which is good, and we found 7 outliers. What would you do if you did this and you found all 10 outliers? What would you do next, apart from worry?
Look for more.
Look for more, because this says these are the first 10. There could be more. In this week's homework, you can find many more than 10, but you'll get to do them. And then, interestingly, it found 2 shifts. It found a shift up in 2008, and this is change in unemployment, and a shift down in 2009, and a bunch of additive outliers. And in a sense, economists would be interested in this just for itself about where we identified the outline. Okay, any questions?
Yes, Dr. Sheetha, sorry, but can you comment on the estimates again? I missed that part.
So all I did, Suz, was go and look at the estimates in this box obtained by SAS and the estimates in this box obtained by JUMP, and just to see how close they are.
Okay.
They should be essentially the same, but we'll see an unstable situation. This is not an unstable situation because these things are way away from the boundaries. This is a stable process that is invertible. Okay? So what should we do next? We're going to write some code like you did on the homework, right? Which allows for 1, 2, 3, 4, 5 additive outliers and 2 level shifts.
Mm-hmm.
So it's the same old code. If underscore n underscore is 252, then the additive outlier is this, etc. Then you have to put in the cross cause. So Diego said, why don't I have parentheses 1 after any of these additive outliers and level shifts? Why is there no 1 there?
Because your dependent variable is already difference.
Yes, we're not doing a differencing in this, yes.
Mm.
Yep. So the cross core is this kind of thing that we'll talk about much more in transfer function modeling. You just have to put it here to get SAS to go. The next line says, estimate a model with AR equal to 1 and MA equal to 2 and predictors, the input. The inputs equal to these additive outliers and level shifts, and please search again for outliers. And please don't find any more because this drives me crazy, all this code, right? So, the good news is it didn't find any more outliers. So what I always do first is look at the value of SBC, -373. Is that an improvement over -327?
Yes.
Yeah.
It's a giant improvement, isn't it? It's like 50 on 300.
Mm.
So that's a beautiful thing, isn't it?
Mm-hmm.
The other thing that I always look at, because imagine I've been fat-fingered, and instead of AO64, it should have been AO46. All of these additive outliers and level shifts are strongly statistically significant. Now, let's look at the coefficients. 0.96 over here without the outliers became 0.97. Did I read that right?
Mm-hmm.
Minus 0.21 became minus 0.16. 0.93 became 0.91. They didn't really change that much.
Mm.
Right? Yes? So what do we need to do next?
Come up with the forecast and see how it is.
Well, we better check that this model is valid first, shouldn't we?
Yeah. White noise.
So, is the model valid?
Yeah.
Yeah, it passes the white noise test, but it's actually sort of worse. It's still valid. So we have a valid model. So let's think about this. We don't want to be too negative, but you know, there's something a little bit wrong with the logic, right? We didn't allow for the additive outliers and the level shift, and we picked the ARMA model before we did that. So I have seen examples, and we will discover one or two this semester. When you go and you put the additive outliers and the level shifts, this thing becomes non-valid. And then what you have to do is go and pick a model that's lower on the SPC list. So this is an unsolved time series problem, to both choose the order and fit the additive outliers and the level shifts together. Okay, any questions about what we've done today? All right, let's move on. Here are some more diagnostics. You can see the points are close to the QQ plot line. Now, what about this wavy line? What do you think about that? Are you concerned with that?
Is it some sort of a pattern in the residuals?
Yeah, so Prerna, this is just one of these things where stat, I'm not concerned, not worried. I'm not worried. So they have to automatically choose the smoothing for that curve, and this is a bit under smooth. If we made the smoothing a bit bigger, that would be the horizontal line. Okay? So I'm not worried. This is a valid model with the additive outliers and the level shifts. Are we good? All right. A question about what, Sam? Yes, tell me. 565, yeah, let's go back to 65. Yes? Yeah, so the additive outliers are going to be 0 going forward because they're just one-off points. The level shifts are still in play because this says there was a level shift after 221 that went on for the rest of the data and a level shift after 234 that went on for the rest of the data. And Sam, the way to think about this is when we look at Chipotle, there's been a level shift down in sales because of their health scares, and that hasn't changed. So this thing is going across at a different level. Now, if another level shift comes in play, then we're out of luck. Now, if you think about the homework I had you do with Berkshire Hathaway, last year I had the students predict 2 quarters of 2016, but that was an unfair task to you because the first quarter of 2017 was an additive outlier up. And you can't possibly predict that ahead of time unless you have another time series which is a leading indicator. That's called transfer function modeling, and Aaron Rubenstein is coming this semester to tell us about that. He actually predicts the upturn in the model because he had a time series as a predictor, which was a leading indicator. Exactly. So imagine, let's say something really simple, Sam. Imagine we have an AR1 process where C is like 0.9. And the last, so that would say that the next value of Y is equal to, let's assume the mean is 0, the next value of Y is 0.9 times the previous value of Y. Now, if the previous value of Y is an outlier, we're going to get a really terrible forecast, aren't we? Yep. Good. Nice question. Thank you. All right. So we're going to do exactly the same thing. Yeah. Okay. More questions, please.
Yeah, this is Adam. Hey, I'm still kind of struggling just to conceptualize how you put this into practice. Let's pretend I'm an economist.
Yeah.
And
sure.
I need
An
to
economist, every day.
and I need to predict, the next 5 years of unemployment. And these models are capable of generating a couple of data points. I'm searching kind of for what's the bridge to get to a point where we can use this for 5 years.
Right. So let's cut to the chase here. So if you and I could predict unemployment 5 years out, we'd be two of the richest men in the world. Okay.
I agree with you on that, but
it's not a feasible thing, right?
I agree.
Yeah. So let's take seasonality. Let's take something that's really simple. We're going to talk about seasonality straight after the midterm, and let's assume that we have monthly data that's strongly seasonal, and what we can do is we can predict. We're in September, we can predict October this year, October the next year, and October the year after that, possibly. So that's like 24 months, okay? So seasonality becomes our friend. Yes? Does that make sense? But all we're learning is that if we have the AR and the MA term with very short, with very small, T and Q are small, it's really only the next couple of terms we can predict. But it is what it is.
Gotcha.
Now, if you can get a transfer function modeling where a lot of the action is, where you can get a time series to predict a time series, and the time series that is the predictor, you can predict sometimes 12 and 24 periods ahead. So Niccolo Casada, who spoke last semester about his project, he's able to predict 12 weeks ahead, and that's that's on the money for what that industry wants. But really interesting question, and you have to keep asking yourself, is this practical? But seasonality will get us out of jail. Does that answer you?
I mean, it's helpful. I just am in a position where we consume data in my job, forecasting economy several years into the future. And I just look at this and go, I'm trying to figure out how they generate it, because it can't be using this type of process, because you would just get flat lines at some point. And so I'm just trying to conceptualize what potentially they're doing, or is there a point in this where, in addition to AR components, you're bringing in other things that may influence, say, unemployment?
Yep, absolutely. That's like a transfer function model. If you bring in other time series, right, that's a transfer function model, and that can potentially get you out of jail.
Okay, that's helpful.
But to build one of those, you've got to pre-whiten the data, it says, where you've got to remove the time series effects from the X's from the Y. So again, it's like we're in elementary school and we're going to get to college by the end of the semester.
Okay, that's super helpful. Thank you.
Thank you. So let's do, we remember ARMA 1.2 was best and ARMA 2.1 was second best. So let's do P equals 2 and Q equals 1. The same code, we're just saying we want two AR terms and one MA term. And here, this really makes me smile, because the first thing is it finds the same outliers. These are the same outliers as we had before. They're almost in the same order. They're almost in the same order. That makes me smile. Sometimes one model will give you more outliers than another. In fact, yeah, it can. Now, again, so if you look at the coefficients in the maximum likelihood estimates from stats in the left panel with those from JUMP in the right panel, they're a little bit different. I mean, they're close. 716, 716, 202, 202, 729, 729. So we're all good. It finds the same 7 outliers. This doesn't always happen. It's actually a little bit rare. So we run the same code. The only difference is we've changed the P equals 1 to P equals 2 and the Q equals 2 to Q equals 1. And the first thing I look at, I scroll down right down the bottom of the output, and you find it finds no extra outliers. Number search 10, number found 0. The second thing I look at is, has SBC gone down? Minus 325 to minus 372. Yes, it's gone down a lot. Are the additive outliers and level shifts highly statistically significant? The answer is yes. And how have the coefficients changed? The MA term was 0.73. It's now 0.81. That's changed a little bit, about 1 standard error. The AR1 coefficient was 0.72. It's now 0.77. That's about half a standard deviation. The AR2 coefficient was 0.2, and it's gone to 0.14. Again, about 1 standard deviation. So in this case, the model's changed a good deal. In the ARMA 1-2 model, the coefficients were very similar with and without the additive outliers and level shift. Is it valid? Yep, it passes the validity test. You know, it's a little bit concerning that we're getting these spikes. Well, it passes. Does it pass? Yes. Am I happy with this pattern? The answer is not exactly, right? There's a lot of lags that, while not significant, they're getting towards it. So we have a valid model. This one is ARMA 2-1 with the additive outliers and level shift. Again, if we look at the further diagnostics, the QQ plot, the plot of the residuals, we say we're good to go. So, at this point, which model would you recommend? Okay, if you had to pick one, which one would you recommend? And how much is better is one than the other?
Can we check the predictions?
Yeah, we can check the predictions, but imagine before we do the predictions. So, Marek, in real life, you send the predictions in ahead of time. You don't know which one's going to do better.
No, like with a holdout data.
Yeah, but the holdout might be we do in the next 3 months, right? So, you know, when we did Chipotle and Glass last year, we predicted the next quarter and it was announced the next week. So, you know, which model are we going to bet our future on?
So, Dr. Victor,
Hold on, somebody cut out there, or there were 2 people speaking. What am I going to do?
lowest SBC
first.
SBC. Let's look at the SBCs on the 2 models, right, after we've allowed for additive outliers and level shift. I'm from the SBC statistical religion. I'm going to always rely on that. So if you go and have a look here, the model which is ARMA 1-2 is minus 373, and the ARMA model which is ARMA 2-1 is minus 372. Which one are we going to pick? We're going to pick ARMA 1-2. Is it really going to matter that much?
No.
I have a question here.
Yep.
Would you take into any consideration, given these are like super similar, like the stability of the parameters with and without the additive and level shift components?
Yeah, you could. Again, it doesn't really bother me. You know,
Okay.
I would prefer if I had to pick one before I did the level shifts, I'd prefer the ARMA 2-1. but no, that's not going to really be a choice. Basically, the SBC, they're pretty close, but the ARMA 1-2 is better, and if I have to pick one, let's pick one. Now, Marek, the good news here is that I have some holdouts, and we'll see who does better on the holdout. Right? Okay? So the next step is to actually forecast. I didn't put the code here, but if you look on the eCampus website, I have put in the forecast command. So this is ARMA 1-2, and ARMA 1-2 says the forecast is minus 0.05, minus 0.06, minus 0.06, minus 0.06. So it says unemployment is going to be going down. Now, what happens with the actuals? Down here? Well, the actuals are minus 0.1. We do pretty good there, right?
Oh, this is the actual.
Yeah. What about here?
Oh, these are the actuals?
These are the actuals.
Okay. Okay.
Yes?
No, not bad.
329, 329, 330, right there, the actuals. This says we keep going down. No, the actual data went up and down. So we didn't do that well after the first thing. Now, one of the things you let me get away with, and I'm surprised you let me get away with it, unemployment rate in all those public sources is only reported to 1 decimal place. So there would be more richness in the data if we could get more than 1 decimal place. Right?
So Dr. Schieder, to play David's advocate here, since you're evaluating the model on prediction, shouldn't you have picked the AIC because you're interested in being as close as possible on the prediction error? You're not interpreting the model?
No, so it's a really good philosophical question, Javier. So all the people I've ever worked with, they want to understand what the model is. They want to understand what the model is. They do not want parameters in the model. So you can, for your own edification, fit an ARMA 5-3 or whatever it was and find lots of things not statistically significant.
Yeah, but what about if this model, let's say you are trading, and this model is a model you use for automatically trading, you don't care about the interpretation, you just want to pick stuff.
Sure. Yeah, absolutely. But I've never been in that situation. If you want to do automatic trading and you don't care about the coefficients, then yeah, blow your hair back with AIC.
Dr. Schieder,
Okay.
how do you interpret something like this though without any other variables in the model? I understand the outlier portion of it, but is that really what you're interpreting?
So what this is saying is, it's saying that the recent past matters. So the change in unemployment, right? If unemployment is going down, it will tend to go down. Look at that AR1 coefficient of 0.9. You see that? Yes?
Yeah, I do.
So again, we're still getting ready for later in the semester. If I want to try and model unemployment and I have some leading indicators, leading time series that are going to lead unemployment, right? Spending. So Adam, you're an economist. What leads unemployment, sir?
Probably interest rates, Dr. Schieder.
Yeah, hold on. Well, I want to answer this question. I'm going to go around the world with everybody. But does anybody know what leads unemployment? What is a leading indicator of unemployment? Adam,
corporate profitability.
Yeah, profitability.
Interest rates.
Yeah, interest rates. There are a whole series of things hypothesized, right? But in order to fit those, you have to be able to, one, as a straw man, come up with a model that doesn't include those. So this is just a step in a piece in the puzzle. Okay? Trust me. All right? So, questions about other issues?
I do. So today I was talking to somebody about a time series model, and they were saying that there are predictors in a model, and I was asking for more information. And they said that the cross correlation is a predictor. Does that make sense?
So when you put predictors in a model, we are going to salivate over the cross correlation. So the cross correlation is going to tell you which forward lag. So if I tell you the cross correlation at lag 6 is important, it says this thing leads another thing by 6 months.
I gotcha.
Okay. Good.
Thank you.
Yeah, so what happens, Sam, is, and again, I'm going to tell you this, and it's going to sound like craziness or way complicated, but we're going to know and love this. So imagine you have, let's just call them Y and X, and X are the predictors. What we're going to do is figure out a series for X, and we're going to remove that series from the Y, and it's called pre-whitening. So yes, we're going to do armors on X's and armors on Y's, and we're going to try and untangle the effect of X on Y. It's complicated, but we will do it, and you will love what we do. But right now, we're just learning all of the tools of the trade. Okay?
Dr. Shearer, could you kindly go to slide 21?
Yep. Can I just finish the deck and we can go back to 21? Is that right? Okay.
Yeah, sure.
So if you go and you look at what happens with the other model, the forecasts are very similar, right? They're almost the same. So basically, in this case, we have two models, competing models that are pretty similar. All right. What slide number, sir?
21.
Yeah,
21.
21. Lucky 21. Lucky one of my lucky numbers. Lucky 21.
It's just a very quick question. On that slide, it says that it can be a stationary or non-stationary ARMA process, but we haven't talked about non-stationary series. Can you comment on that?
Yeah, so again, as you know, Diego, I'm a man of strong opinions, right?
Yep.
So I only ever work with stationary processes. If it's non-stationary, I'm going to difference the thing to make it stationary. Okay?
Is there a process that never becomes stationary, or you always find a way?
I always find a way. So let me tell you what they're thinking about. You could take a process that needs differencing, which is not stationary, and run it through, and it will work. But if you come back, and we're going to talk about this more next week, remember this thing tells you that this is P plus D, right? It's P plus D. So
yep.
If you haven't differenced it, and you should have, then, you've got to take that into account. So yes, you can run the ESHCF on non-difference data. But then when you get to this output, you have to say to yourself, do I need to difference the data? If the answer is yes, then I should subtract 1 from that order. Okay?
Okay. Thank you.
But in my statistical religion, Diego, I only work with stationary series. If you can torture me, but I don't want to do it.
Okay.
Okay? Yep, sorry, I got excited. Any other questions about the deck before we look at the class exercise and the next homework? Okay. Let me pull up the homework. And this was put up this afternoon. So what we're going to look at is what's called, so we're going to take data from the Federal Reserve. I love this website. This is personal consumption expenditures. Right? Personal consumption expenditures. Now, unemployment might be a good leading indicator of that. You know, if you've lost your job, you're not going to spend very much. So if you look at that series, tell me about what you see in that series from 1992. What do you see? The level shift around 2009. What else do you see?
It's not stationary.
Not stationary. It's got an increasing mean. So we're going to look at change in personal consumption. We're going to look at change in personal consumption. I'm going to ask you to fit a model based, find the model based on ESACF, a model based on SCAN, and a model based on ARIMA. Decide which of the models, whether each of the models are valid, and then just fit the valid model. So imagine, I'm making this up. ARIMA model group is valid, SCAN is valid, and ESACF is not valid. You only have to fit the latter two models. I'm going to ask you just to identify the outliers or level shifts, and I'm not going to ask you to go through the process of putting them back in. All right? We've already done that. I just want to make sure you understand the ARMA, how to fit the ARMA piece. Any questions about what is required?
Pretty clear.
Yeah, and I'm making it easy. This is a much longer assignment if I make you to refit the model with the outliers, because you have to go through a couple of iterations. And that's just a lot of busy work for what is not really a good learning experience. Okay? So what I'm going to ask you to do is go to your groups and start working on it. I'm going to be here. If you've got a question, come back to the theatre and Erica will help you ask me a question. Okay?
Dr. Sridhar, we don't have to forecast anything, right?
No, because Tathagata, I'm not making you put the 40 outliers or 20 outliers in and redo it, okay?
Okay.
It's just too long. It's not a good use of your time, okay?
Okay.
What I need you to do is to be comfortable with ARMA process. So you're basically going to do what I did in class for only change in unemployment or change in personal consumption expenditure, okay? All right. So it's just a bit after 8 Central Time. Well, let's say we'll spend 30 minutes on this, or as long as you want. But I'm hoping in 30 minutes you can get the ESACF, the SCAN, and the ARIMA model group going. Okay. So I'll be here with Erica. If you've got a question, please come back and Erica will patch you in. Thank you very much.